Hello everyone, welcome to EduSyn. In this video, we are going to discuss about vertex cover problem using approximation algorithm methodology. Okay, so those who are new, kindly watch the previous videos where we discussed about the reductions. That time where we have already completed somehow about the vertex cover problem to reducible to independent set. That time we discussed like what is vertex cover in depth. We have read that one as well as independent set also we have completed. So let us start with that one like vertex cover problem. So here the vertex cover problem whenever we are working with that. So basically we are going to use the approximation algorithm. The approximation algorithm especially is we are using like we know whenever we are working for the NP complete problems. We found like there are there are many difficulties we are getting. So there are three solutions we can expect as we have already completed in the introductory video. That time we found either the space could be small or might be we can take the small example or the small categorical problems through which we can at least expect the polynomial time, because this happens because of polynomial time. Though we are not getting the polynomial time, that's why we're reading this one. Okay, like we are trying to reduce. If it is not possible to reduce, is there any other way to reduce towards the polynomial? Because polynomial is a time, like you can say big of n to the power k. Okay, k represents a constant. This is what the polynomial time. So nothing, I must not say that one like nothing in the world is polynomial, but I must say something. There is a way through which at least we can achieve the polynomial. Though we are getting it, that's why we have different ways. One of the ways are one of the ways you can say is your approximation algorithm. So the approximation algorithm is a way that we have used. Here basically vertex cover is a part of NP complete. So as I told you, like the first we have a solution like we can take a small one. Second, as we have already discussed, is you can say if similar or a special case of things we can focus like the three sort some problems we can say through which at least we can expect the polynomial. If both two cases which we have already studied, like if both two cases are not there, like there is another way through which at least we can get nearly optimal result. The near optimal result is approximation, which we have already discussed in the previous videos. Okay, so here in the vertex cover problem, this problem basically we are focusing vertex cover in the sense like minimization of picking the nodes. Like we will pick the minimum nodes through which we must say like all the edges connected to the vertex which you have selected is the vertex cover. Here vertex cover, that doesn't mean that only minimum. You can take all the vertex as the vertex cover, not an issue. But the problem is if I take all the vertex in the graph, that is also part of vertex cover. The minimum one is a part of the vertex cover. Here exactly what we are doing, we are working for the minimum one. That is where the problem we are occurring. Otherwise I must say like the E is the edges, V is a vertices of a graph. Okay, if I would like to say like it's definitely I must say big of fun to say for a vertex cover. In what sense? If I say all the vertices which you have is equivalent to the vertex cover, that time I must say because all the vertices are covering means are connecting with the edges. In general you can say I am taking this example of a graph. Clear? This is just a graph, or you can say a tree. I must tell for a graph, all vertices should be connected. Means there is a cycle must be present for a graph. Okay. So if I would like to say the vertex cover, I must say if I'm selecting all the vertices, it's also part of vertex cover, but this is not exactly our target. Is to find the vertex cover is minimum one. Whenever we are focusing on the minimum, like the minimum means the number of vertices which you are selecting should be less. Clear? If I'm selecting A, this will be covered, this will be covered. Clear? If I'm selecting B, this will be covered and this will be covered. So what we'll have to do, like out of this, like there is a three vertices are there. So if I'm picking this one, so I must cover this one also. So two vertices at least needed to complete to say a minimum vertex cover. Clear? This is what exactly we are targeting to find out. So vertex cover, you can say the total edge could be considered. Whenever you are considering total edge, this is a maximum vertex cover. This is not our target is. The minimum size, the minimum one whenever we are discussing, that is a part of here. That is our target. How to define the minimum number of edges to be considered as a part of vertex cover. This is our target. Okay. Minimum vertex cover, I must write that one here. Minimum number of vertices for vertex cover. This is our target or aim and objective, you can say, to find minimum number of vertices required or needed for the vertex cover. Next, I must tell you, like I'm following the book for this problem. I'm following Corman book. You can follow that one. The same to same. I'm keeping the lines and wordings there. So this is an algorithm. You can say the algorithm name as approx vertex cover G. Here C is a set. You can say C stands for the set for keeping the vertices. Keeping the vertices. Next, E dash is the edge which is equivalent to G dot E represents while the number of edges, clear, until it is empty. Means suppose as I have already given you the example. So here this is one graph. Here the edges are 3. Until the edges are 3, like we will run that one, clear. So from this we found it will run for big of E, because while loop we have included. Within that while loop we said until it is E, means big of E, the number of edges we are actually having, that one we can say definitely it's a part of our complexity which we have already completed in our the first the might be the complexity video. That time we have completed to find out the term complexity. So you can say until, so we will return it. Okay, so until means we are just focusing on the number of edges. So here as per the time complexity, I must tell you the time complexity could be big of E. Why? Because the number of edges we are focusing at here, clear. Next, once we started this one, let uv be an arbitrary edge of e dash. We just, whenever we said e dash, e dash is keeping all the number of edges from the graph, clear. So then what we'll do, c was previously is a set, c was empty set, this represents empty set. Okay, so phi, like we'll include, suppose uv, suppose here is av, I'm just writing this one ab. So a comma b, both we will be keeping, because from an edge, if I'm picking one edge will have two endpoints. Here is for that one a and b. Whenever I'm keeping this edge, so here it is written uv, clear. That uv is union, means we added to that the 5 which was previously there. Then remove from e dash every edge incident to either u or v. Means once I'm picking this one, the two endpoints I have, one and a and b. So what I have to do, I have to remove this one. I have to remove this one. What it is written, I have to remove that one. I'm just picking this one. So return C. C is AB. So we are expecting our optimal solutions. First of all, this C is approximation value. The number of vertices are 2. If I'd like to say for this example, the optimal means what should be the answer, what should be our expected answer, clear, means what should be the correct answer for us. So we have already checked that one for optimal value, either ab, ac, cb, anything we can take, but at least 2. So for if this is c, if I'm writing c star, so c star could be the optimal solution, or optimal number of, or optimal set, you can say, if I'm picking, also it keeps either A, B or B comma C or A comma C. So the optimal means whenever you focus on the vertex cover, the number of vertices which you are going to pick is either A, B, B, C, anything you are taking. So that should be 2 also. Here the approximation for this example, as we have already covered in the previous video as an introduction, for this graph, we are saying one approximation. One approximation means which is equivalent to the optimal answer, optimal algorithm or optimal value for this example. For this example, we are expecting the one approximation where epsilon is equivalent to 0, means the extra which we are adding in 2, 3, whatever we are taking. Suppose for 2 approximation, we must say epsilon is 1. Why? Because 1 plus epsilon we have already said in the approximation one. That time we must say for approximation value, if it is 2 means more than 1, suppose we have, so that one more than 1 whatever is there, so we can say it is epsilon for us. Okay, so we will be discussing with the example. So for this example which we just have taken for our approach, for this one we found one approximation for this one, but this is not always correct. Okay, next for the example you can say, suppose this is an example, this is a book example I have kept here. So A, B, C, D, E, F, G, there are almost 7 vertices we have with us, and the edges is 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are 1, 2, 3, 4, 5, 6, 7, and 8. 8 edges are there. So what we are doing? First we'll start arbitrarily. 8 means we will start with a while loop. While loop will run for 8 number of times because we need to remove all the elements, all the edges. The number of edges are 8. So we will take all the 8 up to 5 means 0. Up to 8 we will run. This is what it represents. Arbitrary, it written arbitrary edge. We are not always saying only this one will be picked or this one will be picked number wise. No. Arbitrary. You can take EF also, but as for the book they have taken B to C. Okay, so this edge, once this edge is selected, line 5 which it says the C was previously phi, here C is previously phi, for this one C is B comma C, the 2 elements we have included. Clear? Next, as per 6, remove E dash every edge. Incident means B to C which are connected, we have to remove this one. Just dotted line says we are removing that one. Clear? This is what the C value is. I'm just writing C value here, B and C node. Here, arbitrary again, we have 2 options. We have 1, 2, 3, 4, 5. There are 4 options we have. Because every others are we have already removed. So here arbitrary, as for the book they have taken E and F. So once E and F is picked, now C value will be, previously it was B comma C. Why? Because here it is union. Okay, B comma C, E comma F we are picking. So now C value is updated. Only one we have to pick. There is no other edges are free. Then what we'll do, we have to pick that one, B, C, E, F, D, then G. This is our final, you can say, the vertex cover, okay, which is using the approximation algorithm or approximate vertex cover, you can say. This is our C value. So this one is approximate vertex cover, I can say, using approximate. So that's why I'm just writing uh, approximate vertex cover or AVC. This one is AVC. So which is, we have selected B, C, D, E, F, G. This is our number of nodes or number of vertices we have selected. But for the optimal, which is said as C star, like if you say the optimal means the number of vertices which we are selecting wisely, that should be minimum. Clear? Minimum means you can check, suppose I am picking B, indirectly I am removing this one. Clear? If I am keeping E, I am removing this one, means I am covering. Basically here no removing concepts we should use, we will cover when we are covering, so I am putting tick mark. Okay. Next, if I'll pick D as a vertex to be covered, so here a part of cover we are suppose saying. So for optimal, indirectly what we are doing, so you can check, we can cover all the edges. If I'm saying covering all the edges, I'm just putting this mark. So you can take all the edges should be covered. That's why we can say it's a vertex cover. So here optimally what exactly we are doing, B, E, T. This is not always true, but definitely I must say, as we have already studied in the independent set, that time you can compare one. Okay, so if I would like to say A, that A could at least keep this one. If I'm keeping C, so C will cover this one. If I'm keeping D, D will cover this one, but this edge will be covered by at least one of the uh, vertex. That's why the problem will arise. For the optimal one, means what should be the best answer. This is our best one, best or optimal you can say. Optimal value of vertex cover. Okay, so is BED only. Clear? Though so the problem is not that much hard to understand. The way how we are doing the approximate value or approximation, how we are doing that one, that is playing a vital role. Okay, so I hope you understood. Here we are keeping 336. Here our C value, if I'm saying mod, so it is 6. Here if I'm doing the mod, means the number of vertices, here it is 3. So if you can say, like which we have studied earlier, is a row value. So here is C star, which we must say 2 approximate value or 2 approximation. To approximation. Okay, this is what we have covered. Like the row value is 2 here, and we must say it's approximation, two-way approximation. So I hope you understood this one. Theorem I kept for you. So here in the theorem, basically how to prove it, that matters a lot always. So approximate cover is a polynomial time two approximation algorithm. It just shows whatever the approximation that you have done, polynomial time exactly you are getting, but that is two approximation means it is two times more than the optimal answers. What should be the optimal answer is this one should be the optimal answer, but it is two times more. The approximation value which you got is two times more. That's why it is two approximation. Clear? So proof, that whenever we are starting with a proof, always you should remember what exactly we are representing, like C represented as the set of vertices that you are getting through approximate vertex cover, as we have already discussed that one. Clear? And here they have introduced A. A is just an edge, you can say. Here the cover and edge is A has two endpoints. Okay, like it has two endpoints. So whenever we start with C, C is optimal cover, optimal vertex cover you can say, or optimal cover, set of optimal vertex cover which we have studied earlier. Clear? So here this is the optimal vertex cover or best vertex cover you can say. So it is 3. So like that, what how to basically verify that one. So whenever we say vertex is a minimum one, means there is an end point of A and B. Suppose this is our A. Clear? This is our A. I am just changing that, suppose C with D. The naming convention I am changing. Just try to understand. Suppose this is A, we're having this one. So there are two different endpoints we have. For whenever we say optimal, we have to pick at least one. If I'm saying approximate, for approximate, two endpoints have to be selected. That is what the problem is. Clear? Whenever I must say keeping the optimal one, optimal will keep at least C or D. Any one of this, but at least one. This is what it is written. Clear? Optimal include at least one endpoint. It is clearly mentioned. So definitely A has two endpoints. and here it will keep 1. That's why. Clear? This C and this one first we'll cover up. So this C, whenever we discussed with C star and with the A, what exactly we should have to do? Like for the line 4 means here let U be an arbitrary age. We just picked arbitrary age, which we discussed this one. Clear? So next, once the arbitrary age is being fixed, so optimal cover, we should have the optimal cover. Optimal cover, at least we will pick one of them. So whenever we should say the one of them we are picking up, so this condition will satisfy. Once it is satisfied, next C, which is the approximate value, C will keep the both the endpoints. Clear? Both the endpoints it should have to keep. That's why it cover up with C equal to 2A, means there are two different endpoints we have. So based on that, we will pick this one. If you equate this to like 3.2 35.2 or 35.3, if you are going for equation, so what you will get it like C equal to 2A. This is what exactly you got in 3.5 earlier, 35.3. So you just equate with the previous equation. Definitely you'll get this C is less than equal to 2C star. Means earlier we were just keeping this was our like for C. I must tell uh, first for this example means there is two edges, sorry, one edge with two vertices. So C will keep, definitely we studied earlier like two endpoints C and D. Okay, so C star will be picking at least one of them, either C or D, anything, or D. Clear? So if I am saying this one, so it represents 2 because the number of vertices are this one, and for C star it is 1. It's a basic simple example that through which we can understand. So definitely it is 2 times more, you know, C, that's why you can say C is less than equal to 2 into 1. Why you are saying less than? Might be it is somehow the problem could be the what exactly you are getting. Suppose 1.5 instead of 1.5, you might expect that one. So it is somehow nearly equivalent to two-way approximation. That's why we are saying in this order. Clear? I hope it is clearly understood by you where we are getting the approximation through which we have completed the approximation on vertex cover, and we are getting in polynomial time, but the polynomial time is two approximation algorithm, two times the optimal answer we are getting, but our expectation should be exactly one approximation, but we are getting two approximation. This is what we have completed our theorem. I hope it is clearly understood by you. If any doubt, please comment below. Thank you.